Hello, my name is Ira Bell, and I'm an Astronomical and Planetary Sciences student at Arizona State University's School of Earth and Space Exploration. As of late, I'm interested in objects within our solar system. I wanted to spend some time today discussing an idea that not many people are working on, which is the potential for asteroid mining. For us to contemplate this topic, we should probably take a moment to explain what asteroids are. Well, if you ask NASA, they would say that asteroids are small, rocky objects that orbit the sun. Although asteroids orbit the sun like planets, they're much smaller than planets. Another way to think about this is to simply start with saying something like, not a planet. With space being so vast, humanity has tried to place things into categories to help us better understand them. When I look at the asteroid in this photo, I can almost envision it in motion, heading toward Earth to destroy us all. We're certain that an asteroid hit the Yucatan Peninsula in Mexico over 60 million years ago, and from what we can tell, that same asteroid killed over 75% of life on Earth, including most of the dinosaurs. But most people might be surprised to learn that that asteroid was likely 10 to 15 kilometers wide. While that was a seemingly large rock moving at high velocity, it's actually quite small in comparison to Earth. Earth's diameter at the equator is 12,756 kilometers wide, which would make that asteroid somewhere between 0.000784 and 0.0011% of Earth in terms of relative size. But what about mass? For us to understand the cosmic scale as it relates to asteroids, the Moon would be a better comparison. As of February 27, 2022, the current known asteroid count in our solar system was 1,113,527. That's a lot of asteroids. And scientists have done a pretty good job of estimating the total mass of all the asteroids in our solar system to be around 2.3 times 10 to the 21st kilograms. Yet our own moon is known to be 7.346 times 10 to the 22nd kilograms. So this is where, for me at least, asteroids become extremely interesting. If you were to somehow combine every asteroid together into one object, let's call it mega asteroid, the moon would still have a mass that is almost 32 times this mega asteroid. Another way to describe it is that all of the asteroids in our solar system account for just over 3% of the mass of the moon in comparison. And if that isn't already enough of a change in expectations to most people, there is a second quantitative view of asteroids that we can look at. It turns out that there are about 12 asteroids that take up over 50% of the mass of all the known asteroids, with two of those 12, Ceres and Vesta, covering quite a bit of that mass on their own. I placed a telescope icon in the portion of the chart that illustrates the other 1,113,515 known asteroids. And the reason I used a telescope icon is because I wanted to mention that though it is not necessarily an easy task to look at asteroids, it is actually done quite often. Asteroids have two characteristics that make them more detectable with a good telescope. First, they reflect light. In a moment, I'll cover the types of asteroids by the amount of light that they reflect. But for now, it's just important for us to understand that since they reflect light, we can collect the light through refractor or reflector telescopes, enabling us to detect them and study them. The second characteristic that helps us detect asteroids is their motion, and in particular their motion against the background of stars which don't appear to be moving in comparison. So what do asteroids look like through telescopes? Well, in the image on the left, we can see several asteroid trails from long exposures taken by Hubble, both in the visible and infrared light spectra. The beautiful curves we see are due to a phenomenon known as parallax, which is something similar to when you're driving in a car and the buildings you pass appear to be moving much faster than distant mountains. Because these asteroids shown in this image are much closer than the distant galaxies, their motion is much more apparent to us from Hubble's perspective. On the right, there are two images which are slightly different, and you'd really have to be looking to even notice. I took this image of Messier 104, also known as the Sombrero Galaxy, from my observatory near Yosemite, California, on our 24-inch corrected Dahl-Kirkham telescope. Both images show a crosshair annotation in the bottom left corner, whereby the bottom image shows that the crosshair has moved slightly to the right. Try to imagine a small, faint-looking dot only covering a handful of pixels, moving slightly between exposures. Thus, we have blinking. Observing and studying asteroids really requires a lot of patience, practice, good equipment, and in some cases, luck. So now that we know a bit about asteroids, let's dig a bit deeper and discuss why we would even be interested in mining them in the first place. Well, it turns out that they're an incredible source of things that would be quite lovely to have in abundance on Earth as well as for our missions in space. Using scientific telescopes, reflection and emission spectroscopy, calculations for density, geometry, and more help us understand the composition of asteroids and even let us speculate as to what lies below their surfaces. In fact, a single asteroid may contain enough precious metals that if brought to Earth, would be worth so much in value that it would presumably make those same precious metals have no value at all. As an example, the asteroid 16 Psyche, discovered in 1852, is a 226-kilometer wide metallic asteroid that has an abundance of iron and nickel. There have even been rumors that its core might be made of solid gold. Just to put this into perspective, estimates for the total amount of gold on Earth, both discovered and undiscovered, is thought to be 2.54 times 10 to the 8th kilograms. The mass of 16 Psyche alone is 2.72 times 10 to the 19th kilograms. It's almost unimaginable. As shown here, asteroids contain many elements which would be useful for expanding our presence in space. It's likely much easier, in principle, to obtain fuel for propulsion in space than it is to carry it up, through, and out of Earth's atmosphere. Similarly, expanding space stations or buildings, facilities, and colonies on the Moon, Mars, or beyond would be much easier with the materials present for robotic or human use. It's just illogical with our current technology to launch extremely heavy building and manufacturing materials up using the rocket equation. But if we could somehow find a way to capture and utilize the elements, it feels to me like we would enable a next generation or evolution of humans. It is interesting to think that here on Earth we value certain things such as precious metals and gems because they are so rare. Yet at any given moment, one of our asteroid neighbors may contain more of these rarities than all of humanity has ever discovered. So anyway, some of the things on this list may be obvious with respect to their use, but just a few notable callouts. The volatiles group, hydrogen, carbon, nitrogen, and oxygen, could be used for potable water, fuel, refrigerant, and agriculture. The metals, such as iron, cobalt, and nickel, would be useful for building things. And the platinum group, such as ruthenium, rhodium, palladium, osmium, and iridium, would be extremely useful for advanced materials such as electronics, catalysts for chemical processing, glass and fiber manufacturing, fuel cells, and more. So now that I've hopefully illustrated the usefulness of asteroids, should we figure out how to harness them, we should quickly describe the three types of asteroids. I mentioned that asteroids reflect light in a previous slide, which is displayed here by a term we use in astronomy called albedo. Albedo is essentially the measure of something's reflectiveness. The higher the albedo, the more light that is reflected from the surface. The lower the albedo, there's less light reflected from the surface. So another way to think about this is that snow and ice have high albedos, whereas dark materials, such as dark rocky surfaces, would have lower albedos. In this chart, you can see that each of the asteroid classifications, C, S, and M, have different albedos, though not by an incredible amount or anything. But this measurement, along with other measurements, helps us understand what an asteroid is composed of, and thus enables us to categorize it as carbonaceous, silicaceous, or metallic. So where are the million-plus asteroids that we've discovered? Well, it turns out that they're sort of all over the place. But the largest concentrations of asteroids are certainly between the orbits of Mars and Jupiter. This chart may be somewhat self-explanatory, but I did want to call out the units of measurement for the x-axis, which is astronomical units, also abbreviated as AU. So the Earth is one astronomical unit, or AU, from the Sun, which is around 150 million kilometers, or 93 million miles away. So with each iteration of an AU, you can essentially double that number. You can see the largest groupings of asteroids tend to fall between 2 and 3 AU. The other axis shown here, the y-axis, is the inclination of each plotted asteroid. It's not important for this lecture, but I just wanted to mention that inclination is related to the position of an object's orbit in space as it relates to another orbit. You might think about an ant walking around an apple in a straight line. That could be, if you follow orbital logic, the ant's orbit. If you were to pick the ant up and place it somewhere else on the apple, and the ant would continue to walk in the straight line, the ant's inclination might have changed. That's quite the oversimplification of this notion of inclination, but suffice to say that asteroids are largely grouped by distance with varying orbits, orbital periods, rotation speeds, and more. So have we ever conducted any missions to make contact with asteroids? We sure have. NASA's OSIRIS-REx mission was established to make contact with asteroid Bennu and obtain samples that we could bring back to Earth. In fact, the hardest part of this mission has already been a success. The OSIRIS-REx mission team has successfully landed a spacecraft on Bennu and gathered samples. The spacecraft then launched off of Bennu and started making its way to Earth on a 2.5-year journey. We expect it to arrive September 24th, 2023. On the top left photo, you can see the spacecraft. And the other images shown are the images of asteroid Bennu itself. It's extremely interesting to see piles of rocky rubble, boulders, and the like. So what would that look like if we were to stand on it in person? Well, this image of Bennu was taken by the Polycam camera on NASA's OSIRIS-REx spacecraft on March 28, 2019, from a distance of 2.1 miles, well, 3.4 kilometers. The field of view is 162.7 feet, or 49.6 meters. For scale, the large light-colored boulder at the top of the image is 15.7 feet, 4.8 meters tall. I've done my best to place humans to scale by the known size of the top boulder for reference. That looks like it would be an extremely difficult hike. And I mention this not only because is it important for us to think about what obstacles we might encounter if we try to land things on asteroids, but so that we also begin to think about how challenging it might be to capture some of this precious asteroidal material for our uses. In another example, the Japanese State Space Agency executed, with their partners, the Hayabusa 2 mission where they landed on asteroid Ryugu and collected a sample. I should note that I'm almost assuredly mispronouncing the name of this asteroid, so I apologize for that. Ryugu. I did look it up and attempt to practice its pronunciation, but my native English-speaking background has made it nearly impossible for me so far. In any case, this was a highly successful mission. The collector landed on the asteroid, collected samples, and returned to Earth for scientists to study. Absolutely incredible and well done to the Hayabusa 2 mission team. The two images of the asteroid shown here also show a rocky surface with large boulders and cliffs. You can see the human I've added in for relative scale. So now let's talk about collecting these materials. The mining portion itself, if you will. Well, if we look at one of the many methods we've used to collect materials on Earth to date, we have several things that we have working in our favor. For example, gravity on Earth is all we've ever known until we had amazing revelations from Kepler, Newton, Einstein, and beyond. And while we might not think too much of gravity when we're digging a hole, it turns out that it's really important. For example, gravity on Earth is 9.807 meters per second squared. And the largest asteroid, Ceres, at a diameter of 946 kilometers, has a gravity of 0.28 meters a second squared. Frankly, this is a problem for mining as we're used to doing it. You can't expect a drill or an excavator to operate as they would on Earth. You might think about an excavator sitting on the asteroid surface, as shown here in a picture of an Earth-based mine, but when the operating arm attempts to excavate something, the treads or tires just lift up and away from the surface. Similarly, asteroids don't have anywhere near the atmospheric pressure that we have on Earth since they lack atmospheres. So just these two items alone make mining operations as we know them quite complex. And I suppose I should mention that even if things like drills and excavators could work as normal on the surface of an asteroid, the number of debris and rubble floating around, presumably colliding with things, would be extremely hard to deal with. So here we have 4 asteroids on display, which are in fact the largest asteroids in our solar system. Ceres, shown here, as mentioned earlier, is our solar system's biggest asteroid. In fact, it's only slightly bigger than the height of Florida. In fact, I've done my best to emphasize this comparison to the height of Florida against Ceres with the annotation showing a pair of flip-flops or sandals. We actually know of asteroids which are less than 10 meters or 33 feet across. The gravity of each of these asteroids is shown in each of the asteroids' center. Atmospheric pressure is about as close to zero as you can get. There are some other issues with respect to asteroid mining that I wanted to mention. They're called out in this slide, but the main thing to think about is that if we're landing on an asteroid, even the biggest ones in our solar system shown here, we are subject to an incredible number of risks that we need to calculate and plan for. I did want to mention, though, that the gravity being such low gravity and the lack of atmosphere makes it somewhat easier to leave asteroids. For example, Earth's escape velocity is 40,284 kilometers an hour, and the Moon's escape velocity is 8,568 kilometers an hour. As you can see here, the largest asteroid, Ceres, has an escape velocity of 1,855 kilometers an hour. So definitely much easier to launch away from asteroids from that perspective. Before I move on, I wanted to note two fun facts about asteroids. First, some asteroids have their own moons. Amazing. Second, some asteroids are believed to have had liquid water on them at some point. This is likely due to an asteroidal impact whereby one or both of the colliding asteroids had ice as part of its composition, and the resulting heat from the impact enabled the ice to change state to liquid. Clearly, without an atmosphere, the water wouldn't last too long, but it is quite interesting to think about stumbling upon an asteroid with a river or body of water. Since we've discussed gravity on Earth, as well as a selection of the largest asteroids, we should discuss the two celestial objects that come up often for planned spaceflight. While there is more gravity on Mars, it takes 9 months to get there with our current technologies. And NASA's assumption is that we'd need to spend at least 3 months on the planet preparing for the proper return, making the total round trip, if all went well, 21 months. And though there is gravity, the surface conditions of Mars aren't necessarily exponentially more favorable. The atmospheric pressure is still over 150 times less than that of Earth at sea level. So what about the Moon? It turns out it's not necessarily that great either, in terms of atmospheric pressure or gravity anyway. But the gravity is certainly much better than that of asteroids, and it's large enough to orbit such that we could have several things in orbit as a staging environment for various operations, such as mining operations, refueling, scientific research, preparation for interplanetary human travel, and most importantly, it's close. The Moon is on average about 384,399 kilometers, or 238,855 miles away. That's much, much closer than Mars, which when we average its range and distance from Earth is about 228 million kilometers, or 142 million miles away. I want to briefly cover two technologies that have been discussed with respect to asteroid mining. The first is the Hall thruster. This is a solar electric propulsion system that has been in research and development for over 50 years. In fact, we've even had successful test fires of this technology. What's interesting about it are two key points to me. The first is that it has the potential to increase spaceflight transport fuel efficiency by 10 times our current technology. The second is that the technology for the Hall thruster designs use inert gases such as xenon or krypton, which means that there's no risk of explosions or combustion. That sounds like a great win with respect to asteroids. Personally, I feel if we can enable more transport with cheaper and more efficient fuel around asteroids and ensure that the fuel isn't going to explode if, and dare I say when, we have some type of accident on a given mission, that's a good situation. So anyway, these engines are also referred to as electron and ion thrusters. They don't produce a ton of thrust in terms of what would be required to leave Earth's atmosphere, but kind of think of it like this. If you had about 50 quarters, as in the American currency in your hand, that would be kind of relative to the thrust of one of these engines. It's not so good for Earth, but in space, that's fantastic. Believe it or not, it could really get a spacecraft moving. The second technology or idea I wanted to mention is the idea of some type of cargo net or parachute-looking apparatus which would essentially wrap itself partially or entirely around a given asteroid, so that we would then have an opportunity to try to conduct surface mining or perhaps enable small explosions with just enough precision to not destroy the cargo net, but to release the material which we could then collect. There are several technologies out there that have been discussed by scientists and engineers, such as the use of lasers, chemicals, and even a really neat idea of following behind a comet to collect the contents of its tail. But at this time, we're still working on learning more about asteroids in hopes to understand their origins, composition, and how they fit into the picture in the magnificent and inspiring vastness of space. Thank you for taking the time to listen to my lecture. The telescope shown in this image is the telescope I used to capture the image of the Sombrero galaxy shown earlier. Please feel free to reach out to me at any point. Thanks again.